morning, everybody, and thank you for coming back to my lectures on general aspects of superconductivity. And today we will discuss about what type of measurements do we usually perform to get some information about the superconducting properties. Okay, so in the first lecture, I will show you results and how we do transport measurements, and also what things can obtain from DC magnetization. So I will show you transport measurements, DC magnetization, and also some results from DC magnetization relaxations. Welcome. Please fill the first desks. No, not in the back, not in the back. Every place which is on front, please be filled. Okay. Now, transport measurements. For transport measurements, we need contacts. They are rather easy to make if we have wires or tapes, and for that we can need just some soldering at low temperatures using some alloys based on indium. It is also quite easy for bulk and metal textured high DC superconductors, and for that we use the silver paste and then cook them all, and we get quite nice with low resistance contacts, but they are quite difficult for films. For that kind of films I showed you yesterday with filling centers, for that we need to use photolithography, and specifically there are some types of photoresist. We use some equipment for optical exposure, and this is the type of the equipment. We have to use a mask aligner, and we have to use a developer. And after that, after we are doing this, we need to etch, to cut trenches into the material in order for getting bridges which have not very high cross-section, because a large cross-section with that huge critical current densities we have, it means we need to put a huge current inside. First of all, usually not everybody has such current sources to put inside 100 amps or something. Second, you will use a lot of power in your lab. And third, you might very easily fry the contacts because you lose a lot of energy at the contacts, and also that thin wires have problems. So that's why we need to produce micron size bridges. Okay, so this is the equipment using for mask alignment. And here it's an overview. So this has been done on a 5x5 millimeter YBCO film. After etching, we have 4 bridges. They have roughly the same length of about 0.5 millimeter, and we have thicknesses from about 50-60 microns, smaller, and the last one was eaten by the etching system, so this one was destroyed. But this was the thinnest one we could work on. Okay, so this is an image of the thinnest one we can get. So this is the superconducting bridge. Here are the voltage contacts, and here furthermore are the current contacts. And what we do, we pattern them with 4 wires connection on a sample board. So if you look here, this is 532 micrometers length, and the width is something like 34, 35 on this one. This was the smallest one we can get, 6.32 micrometer. So after we pattern them, we make contacts. For contacts for this bridge, of course, we can make contacts for all of them if we have the system in order to measure, let's say, 3 samples on the same time. And after that is the rotating platform with a thermometer from the PPMS. This is the quantum design physical properties measurement system. You can get them with 14 Tesla, you can get them with 9 Tesla, you can get them with 7 Tesla, depending on the DC field which can get. The price also varies. Anyway, it's about $500,000, a good system with many options. So this is the option which is called rotator. So you have also DC resistivity sample board. So you put the sample here, make contacts, use a tool, and put it inside your dual or cryostat of the PPMS. You can also have the AC transport sample board, which is this one, and you mount it there, and with the electronically controlled movement, you can change the angle between the applied field and the surface of your field. So this is what we need to use to obtain data about the anisotropy of the critical current in respect with the applied field. So this is a typical PPMS system. You put the sample inside, and here is the control board with computer and so on, with DC field, so on. The other equipment which is sold by Quantum Design, the Quantum Design Squid, no, this is the Squid MPMS, magnetic properties measurement system, but the PPMS look rather similar. So I have a picture just for the Squid one, NPMS, not PPMS. In the rotation measurement of the YTCO bridge, we all the time use the maximum Lorentz force configuration. And what can we get now from this type of measurement? First of all, we obtain resistivity versus temperature. And from here we can obtain critical current, critical temperature as function of applied magnetic field. And here are some examples. So if we measure with field parallel to the z-axis, this is TC, the resistivity drop at different fields. And this is for a various economic Doppler DCO field in magnetic field from 0 up to 6 Tesla with field parallel to the z-axis. You see that TC goes from onset, but let's talk about this one, about 89 goes to 81 at 6 Tesla for field parallel to the z-axis. And for field parallel to the AP plane, we go from 89 point something to 86. So you see that for this type of fields, actually the superconductivity at these fields is better along the AP planes. Let's go back a little bit at the phase diagram of high temperature superconductors. So here is the low DC superconductors. You just have Meissner phase, mixed state or vortex state and normal state. Now forget a little bit about this one. This is the phase diagram for highly anisotropic high DC superconductors, BISCO. This one has this reentrant melting. For YDCO, for example, the melting line is very simple. So here, if you have temperature, and here you have the magnetic field, HC2 is something which is not very relevant for high DC superconductors because of the high temperature. High temperature meaning we have large thermal fluctuations. So what we have here, we have up to HC1, we have the Meissner state, and from here, this is vortex liquid and this is vortex solid. I explained to you yesterday what does it mean solid, what does it mean liquid. Now, in vortex liquid phase, resistivity or dissipation is proportional to the current. in the normal state, also resistivity is proportional to the current. Only the constant in front of current is different. So here will be the coefficient for normal state, voltage dissipation, sorry. Voltage or dissipation proportional to the current. Here will be the normal state resistivity. And here will be some sort which is called flux flow resistivity, which is smaller than this one. So here we have a linear dependence of dissipation or voltage on the current, but also here we have a linear one. So linear dissipation, linear dissipation. So what happens is the crossing between vortex liquid phase and normal phase is not a phase transition. It's just a crossing, something you slowly make. If you have some honey. So a cold honey is here in vortex liquid. You can take your spoon and will go slowly down. If you warm your honey, it will become more like milk and will fall much faster. So this is the crossing from vortex liquid phase to normal phase. So it's not a phase transition, it's just a linear gradual transformation from one type of resistance to another type of resistance. The real transformation happens here. So here is the region in which you can use the superconductor as dissipation-free mean to transport current. Okay, so this is the main difference between vortex liquid. We have linear dissipation, the electric field proportional to current density or voltage. Vortex solid or vortex glass will have a strongly non-linear dissipation. Electric field or voltage goes as exponential of minus gt over j. Jt is the threshold current, the constant for every material, at an exponent mu. So what you see here, if j decreases linearly, the dissipation decreases much faster, exponentially. So this is the mark of vortex solid. So in the case of highly anisotropic superconductors like VSCO, vortex liquid region is much larger than in the case of YBCO, and also you have the reentrant liquid here. Okay. So from transport measurements, we can really obtain the vortex melting line. This line, which I showed you, is very important. This is the one which is important for practical applications. Now, let me show you something else here. How is an IV curve if we look it in linear state? Okay. So this is voltage or electric field, and this is current or current density. What we have here for a normal material, we have something like this. So this is a normal material. So it starts from zero, current zero, voltage zero, and it's linear. And the slope is the resistance or resistivity if we discuss about electric field or
one small correction is the unit will be volt.
No. You can plot it here voltage or electric field, doesn't matter.
Okay.
No, it's not unit. E or V.
All right.
Here you can plot either current density or current, doesn't matter. If you have in one case the slope will be resistance, in the other slope, in the other plot the slope will be the resistivity. So this is for the normal metal. What will be for Semiconductor. Semiconductor is also linear, yes? That will be going like this. Semiconductor. How would it be for a superconductor? Well, for a superconductor, we know that at low currents, voltage is zero, yes? So we will start here. At some point, it starts to deviate from this one, and is deviating like this. What will be happening further? Will it go like a semiconductor? Yes or no? No. We'll go like this. We'll join the normal one here. And here, it is the depairing critical current. Here is the current which will break the Cooper pairs apart. So this is the normal, a linear scale. In a logarithmic scale, you will see something like this. Okay, so what we have here is for a single grain of YBCO in 0 Tesla, in 2 Tesla, and the difference between each curve is probably 10 or 20 millikelvin. So each line, each ID, you see these are plotted in log-log scale, yes? So this is the normal scale IV curve, and if you look at the log-log plot, we start here from low temperatures, here are high temperatures. The difference between each curve in terms of increasing temperature is the same. So what we see here we see many IV curves which goes on top of each other, and we are around here when we approach the normal one. Then we have, but you see the curvature is like this. It goes down like this. So here we are in the vortex liquid phase. Here it's again a linear slope, but now it's in the log-log phase, and that slope for bidimensional system, it's the Kosterlitz-Dowless transition, and the slope will be 3. Here you see at lower temperatures, the curvature goes down. So here you see we have 10 to minus 9 volts. So we have used a very sensitive squid picovoltmeter to manage to obtain these values here. So what you see is, for example, this one which has a downwards curvature. If you can go down as much as possible, you see you will not go to, you will stop with the current at some place. So when you have this kind of down temperature, you know that you're in the voltage solid phase, and you will have a critical current. Here, it's in the vortex liquid phase. You see it's upward curvature, and if you go down, you will get very small, going to 0 critical current density. Similar IV curves for an artificial superlattice. This work has been done in Southampton, and this has been done in Rome 2 years after that. Here you see that's the vortex melting line between vortex solid and vortex liquid. The dotted lines at different fields are, and from this one you can find melting temperature for each field. So for this field we have this melting temperature, for this field we have this melting temperature, and so on. If we repeat that, we can get points on this vortex melting line. What else can we play with this? So above the melting temperature, which is a function of field, we have a crossover from an ohmic behavior at low currents to a power law relation at high currents, and then the IV curve displays an upward curvature. Below the melting temperature, the IV curves show an exponential relation at low current and the power law behavior at high current with a downward curvature, suggesting that the system approaches a truly superconducting phase vortex glass for currents exponentially small. Now, it is a seminal review paper by Fisher and Hughes in a PRB, I don't know exactly the year, but they can also do some sort of scaling. So they find out that the whole IV curve displays a power law relation which takes this value, and Z is the critical dynamical exponent of the vortex glass, and D the dimensionality of the system, 3 in this case, meaning 3 in terms of YBCO and then superlattices. Above the melting temperature for low currents, the ohmic region in the IV curves, and the resistance can be scaled like this, where nu is the static critical exponent. So this was a discussion in terms of the critical phenomena, first introduced long time ago by Landau and then by Landau and Gisborne. So what happens is that we will have a Fisher and Hughes scaling, meaning if we make this relation V divided by current, 1 minus T over T melting, at the power nu multiplied by Z minus 1, this will be a general function, but with 2 branches, F plus and minus, current divided by T, 1 minus T over Tm to nu. So what we do, we transform voltage into this relation, current into this relation, and put all our IV curves at all temperatures, and all of the IV curves which are in the vortex liquid phase will collapse on a single universal curve, and all our IV curves which are in the vortex solid phase will collapse on another universal curve. So this is very, very nice image of this Fisher-Hughes scaling. You see different fields, different melting temperatures, but the scaling looks quite nice. Okay, what else can we obtain from transport measurement? Something which is very, very important, especially for applications of polyconductor, and that's the angle dependence of critical current. I've showed you what the equipment looks like and how the rotators are. And here I'm showing a bilayer containing a quasi-layer of silver nanodots grown using 50 laser shots. Now, to imagine how little silver we use in these quasi-superlattices, for growing this is not millimeter, this is 1 micrometer, so this is a micron. To grow 1 micrometer YBCO or bioluminescent doped YBCO, we need 6,000 laser shots. So obviously these 50 laser shots of silver will create just some small nano islands on a quasi layer. So you see at low fields from that rotation transport measurements, we have seen that for this type of fields, for example, at between 0.02 Tesla and 2 Tesla, we see that, no, let's look at this at 77.3, because this is important. We see that for 2 and 2.5 Tesla, the current, when you apply the field parallel to the z-axis, the critical current is larger than in the AB plane. So this is something which is opposite what happened in single crystals or in undoped YBCO. And as you increase the field, you see that at about 2.5, we have a very, very small anisotropy of the critical current. So in a single crystal, if you put the field parallel to the C-axis, you will have the critical current 5 or 7 times smaller than in the case when you put the field parallel to the AB plane. So here is the opposite. When you put the field perpendicular to the C-axis, to the AB plane, the critical current is larger. So what does it mean, such small anisotropy of critical current? As we discussed yesterday during your question time, depending on the equipment you are doing, the type of solenoid you would like to be sure that parts of your solenoid which is subjected to applied field at different orientation will not surpass critical current on that direction. So if we are sure that regardless of the angle, critical current is almost constant, which is this case, this is what we need. So for an application in which you expect to have 2.5 Tesla, then if you put 10 to the 5th amps per square centimeter, then you are sure that it doesn't matter what the field orientation is, you will not subject piece of your equipment to current larger than its critical current at that orientation. Now, if you move to higher fields, of course, you will go back to the normal situation in which the critical current is larger for field parallel to the AB plane. This is some other images at 82 Kelvin. This is another 3-layer film which you see the values, but now I plot it in the critical current as amps per centimeter width. So you see that if you need to work at 2 Tesla, you can easily put 50 amps in 1 centimeter width, and you will not surpass the critical current for that orientation. Okay, what else can we do? DC magnetization. We explained yesterday how can we get JC from that, from this equation in the case of thin films. These are some examples, and this is critical current as function of magnetic field for some of our vast superlattice. You see that we have grown very thick film to maximize critical current, and these dots are maximum critical currents obtained by other groups in Europe, which they concentrated on increasing critical current density and not growing thick films to increase also critical current. Also from DC magnetization loops, we can obtain the bulk pinning force, and what we plot here is the pinning force, which is the magnetic field multiplied with critical current at that field. And we divide by the maximum pinning force, so here we have 1, and we can do that analysis we have discussed yesterday, trying to add and not to convolute the formula for 2 or 3 types of pinning centers. So in this case, the best fit was if we well, first of all, you look where the maximum is. If the maximum is close to 0.2, you will have the majority of pinning to be surface normal, which was the case here. And then you try to improve the fitting by adding some other types of pinning, and through trial and error, this was the, let's say, the ratio of types of pinning centers in this particular sample. 90% surface normal, 8% point normal, surface delta K 2%. Now let's go back. You see, okay. Now you see here what are actually the values of critical current density. 10 to the 4, 10 to the 3, and so on. What does it? Yes, please.
May I ask a question?
Yeah, sure.
Is it possible to identify film growth orientation by considering the angle dependence of the critical current in this case?